So let's now put this in the observational context and work out how you could try to observe SZ effects. There are three principal techniques, one using interferometers, and as we know, interferometers are excellent for measuring structural information. You could try to use single dish radiometers, which integrate over a single beam, and that can be quite fast for a single object, single pointing measurement. Or you could try to use bolometers, particularly a bolometer array, and that's the more modern technique that has been adopted for surveys for SZ effects. Let's take this from the top. The first interferometric radio image that was published is that of Abell 2218. This is that picture, fairly rough looking image, where the black blob at the middle is the SZ effect as measured at a few centimeters. The brightness of this agreed with my single dish data, but the key point about this image was that there's very little structural information. The blob at the center is almost exactly the same size as the synthesized beam of the measurement. That is, there's very little angular dynamic range. You can't look at substructures. Typically, that's what has been found with interferometers. Here's a series of SZ effect maps of a number of clusters ranging in redshift from about 0.2 to around 1. All of the clusters were easily detectable. That's to do with the redshift independence of the SZ effect. And interferometers are very good for pushing up integration times by by just adding in multiple passes, and hence getting very high signal to noise. But in every case, the beam, as you see in the lower left ellipses, is not that different from the size of the SZ image that's been detected. Again, there's a restricted angular dynamic range. Let me explain that using an example of trying to plan an observation for Abell 665 using the VLA. The black line on the right shows the visibility function for Abell 665. You get all of the signal if you just integrate everything together, that is zero baseline. But as you push the antennas apart, the fringes tend to cross the cluster gas distribution a number of times, and they tend to average out. The VLA antenna size restricts you to baselines greater than about 700 wavelengths at this observing frequency. And that means that the best you can hope for is to see around 12 or 15% of the central SZ effect. That makes measuring the total effect rather problematic, because you're going to be extrapolating to a total effect from a subset of the information. What this is very good at is rejecting any radio sources that are within the cluster, because some of the very long baselines way off to the right-hand side of this plot measure those radio sources, and you can subtract them out fairly trivially. The nice thing about that is that if the radio sources happen to be variable, you measure them at the same time as you measure the SZ effect, and so can subtract them out coherently. This is what an interferometer designed for SZ effect work looks like. This was the SZ array located in the Sierra Nevada in California. Antennas quite small, packed closely together and integrating away happily. This telescope no longer exists. It was found that bolometric methods are more efficient at producing a lot of results in a short amount of time. And here is an illustration of how much you can push the technique to high redshifts. This is a cluster at redshift 1.9 that we found with the XMM XXL survey. And on the left-hand side is the SZ effect image. Clearly, you can find SZ effects out to extremely high redshifts. The strange thing about this SZ effect image, where the SZ effect is in colour and the X-rays are in the white contours, is that the SZ effect is coming from the southern side of the cluster rather than being co-located. The effect is shown on the right-hand side in the two sets of contours on top of an optical image. We were looking to see whether there was any evidence of a collision going on here. The results were inconclusive. The simplest way of measuring one of these signals is just to try to look at a cluster and average it, add everything up in a single beam, using a single dish radiometer, preferably with multiple beams. This can be quite fast if you're trying to measure the SZ effect of a single cluster, but it hasn't changed very much since I used it back in the 80s and early 90s to make the first systematic SZ effect studies of a number of clusters. The plot on the right shows a figure from a paper I published showing 3 clusters of galaxies where the SZ effects are shown to be coincident with the X-ray centers of the clusters and not necessarily the optical centers, which are indicated by the vertical black line. The problem with this sort of technique is that if there are compact radio sources emitting on top of these shadows which are decreasing brightness, the things tend to average out. You have to have a way of getting rid of those radio sources. And radio sources tend to cluster in clusters with their galaxies. The modern method is to use bolometers, particularly bolometer arrays. Bolometers are great because they have extremely wide simultaneous bandwidths, or can have, and so can give you extremely sensitive measurements of the brightness of the sky. They can be a bit of a problem in that the brightness of the sky changing causes the nature of the signal you get to change, and atmospheric transmission at typical frequencies where bolometer arrays work in the millimeter are not perfect for ground-based sites. Space-based sites are ideal for bolometers, and the Planck survey is one example of these. What does a bolometer array look like? Well, this is the interior of a bolometer array under construction, where there are a lot of single horns being put together on a cold plate. Those are those reddish things at the top. This was going to be a 300 element bolometer to go at Chajnantor in a project run by the Max Planck Institute. This is a prototype for the Apex 300 element bolometer. It worked at 0.87 millimeters and could make SZ effect measurements. Here's another example. These are some measurements I made using SCUBA on the JCMT in Hawaii. 2 clusters. The one on the left shows a faint SZ effect. The one on the right doesn't. You can't tell by eye. It's quite hard to see. The SZ effect at these wavelengths is a positive effect rather than a negative effect. So you always have to worry as to whether or not star-forming galaxies in the clusters are providing extra signal which is enhancing your SZ effect incorrectly. Here's a nice picture from the MUSTANG instrument on the Green Bank telescope showing a nice SZ effect in a cluster that's accessible from Green Bank in the north. Here the SZ effect is shown to be extended east-west, And again, there's an issue with the alignment of the SZ effect with the underlying known cluster structure. Perhaps, again, because of intermittent heating of parts of the cluster by collisions. I wanted to put this slide in to show that the Planck cluster candidates drop off very strongly in number as you go to higher redshift. You can't rely on Planck to find your favourite cluster at redshift 0.8, for example. The reason for that is that the Planck beam was simply too big. The clusters only fill a small fraction of the beam, and so the signal you see on the sky tends to become dominated by the background, the microwave background outside the cluster, rather than the shadow signal coming through the cluster. This can be shown another way against some other surveys. The Planck sample are the black spots, and the red circles and squares are from ground-based telescopes with much smaller beams that can push out to higher redshift. At lower redshift, Planck is very much superior. At higher redshift, if you want to get to a moderate cluster mass rather than looking at one of the huge, most massive clusters in the sky, you have to use a much larger antenna and an angular resolution of better than about 1/4 of an arc minute. Planck was capable of getting to about 4 arc minutes. Now, what I want to emphasize about the SZ effect is that it is inherently a rather unbiased way of studying clusters, in that it gives you an integrated measure of something real about cluster properties, like energy content, whereas the X-rays tells you something about a merger of X-ray content and central concentration. For that reason, improved SZ effect data, such as are going to come from the Simons Observatory in the fairly near future, are expected to tell us a lot about clusters. The outer structures, and looking for shock fronts from cluster-cluster collisions through the thermal effect. One can hope, indeed, to look for the energetics of gas in radio sources by using the so-called non-thermal SZ effect, which is the relativistic version of the thermal effect from the gas in clusters. You could look for the radial velocities of clusters using the kinematic effect. You can look for transverse velocities of clusters using either the intensity effect or the polarization effect. The Birkinshaw-Gull effect comes into play here. And it's possible, with the sensitivity of the Simons Observatory, to start to detect the infalling material, the filaments of gas that are dropping into clusters as structure forms. So I would say that for the SZ effect, the shadows of the microwave background radiation, the future is bright, even though the effect may not be. Thank you for your attention.